Welcome back to Talk Tensors, where we like to break down the latest and greatest in machine learning research. Today, we're diving into a paper that tackles this question. It's a question that's both fundamental and incredibly timely. How do we actually understand what's going on inside these huge language models? The ones that seem to be taking over the world.
Yeah, it's a question that's been keeping a lot of researchers up at night, that's for sure.
And the paper we're exploring today, it offers a fascinating approach. Using something called Sparse Autoencoders, or SAEs for short. The paper itself, it's called A Survey on Sparse Autoencoders, Interpreting the Internal Mechanisms of Large Language Models. And it's like a treasure map to this exciting area of research. Now, before we get into the nuts and bolts of SAEs, let's set the stage a bit. Why is understanding LLMs such a big deal? And why do we need these specialized techniques like SAEs to do it?
Well, LLMs have become incredibly powerful. They're capable of everything from writing code to composing poetry. But the thing is, their inner workings are still largely a mystery. They're like black boxes. They take in data, they spit out results, but we don't really know how they're making those connections.
Right. It's almost like we've created these brilliant AI chefs. They can whip up these gourmet meals, but we have no idea what ingredients they're using or how they're combining them. And that's a problem, especially as we start relying on these models for more and more critical tasks.
Exactly. If we're going to trust these models with things like medical diagnoses or legal decisions, we need to be able to understand how they're arriving at their conclusions. We need to know what factors they're considering, what biases they might have, and how they might behave in unexpected situations.
So that's where SAEs come in. They're like those curious culinary students who are determined to reverse engineer the chef's recipes, figuring out the key ingredients and the secret techniques.
Yeah, a very apt analogy. SAEs aim to break down the complexity of LLM activations. Those internal signals that fire as the model processes information into smaller, more understandable concepts or features.
Okay, let's unpack this idea of concepts a bit. What kinds of things might these SAE-extracted features represent?
Well, imagine anything from basic grammar rules to sentiment analysis, recognizing named entities like people or places, or even higher-level concepts like understanding irony or sarcasm. What's fascinating is that SAEs can uncover these hidden gems without needing us to label the data beforehand. They learn directly from the model's internal activity.
That's pretty mind-blowing. It's like they're reading the AI chef's mind, figuring out their thought process, and then translating it into a language we can understand.
Precisely. And as the paper highlights, this translation can reveal some truly surprising things about what LLMs are actually learning. For example, when researchers applied SAEs to Claude 3 Sonnet, they discovered this feature that was highly active when the model encountered language that was excessively flattering, even if it wasn't necessarily sincere. They called it the sycophantic praise feature.
Sycophantic praise?
Yeah.
That's intriguing. You mean LLMs might be learning to recognize and maybe even generate different forms of manipulative language. It's like they're developing a sense of social strategy. This has some pretty interesting implications for how we think about AI and its potential impact on human communication.
It certainly does. And that's just one example of the unexpected insights that SAEs can provide. But before we get too deep into those insights, let's take a step back and explore how this whole field of research evolved. The paper provides a fascinating timeline of how SAEs came to be. And it all starts with a rather simple but ultimately flawed approach.
Oh, I love a good origin story. So where did this quest for understanding LLMs begin?
Well, in the early days, researchers thought they could just examine individual neurons in the model and figure out what each one represented. It seemed logical, find the neuron that fires when the model sees the word cat, and voila, you found the cat neuron. But the reality, as you might imagine, turned out to be far more complex.
The classic case of oversimplification.
Yeah.
What went wrong with this neuron-centric view? Did they end up finding that cat neuron?
Not quite. As they delved deeper, they discovered that many neurons in LLMs are polysemantic, meaning they respond to multiple, seemingly unrelated things. It's like trying to crack a code where the same symbol can represent different letters depending on the context. So one neuron might fire for cat, but also for dog, fluffy, and maybe even existential dread.
Talk about a mixed bag of signals.
Yeah.
So trying to pin down individual concepts by just looking at single neurons was like trying to understand a symphony by listening to just one instrument. You're missing the full richness and complexity of the composition.
Exactly. And that realization led to a shift in focus from individual neurons to groups of neurons. researchers began to suspect that maybe a specific combination of neurons rather than a single neuron held the key to representing a particular concept. And that's where the idea of sparse autoencoders began to take shape.
It's like realizing that to truly appreciate the symphony, you need to listen to the entire orchestra, paying attention to how the different instruments interact and harmonize. So how did SAEs first prove their worth in this quest to understand LLMs? Was it a gradual process, or was there a pivotal aha moment?
Well, the initial successes came from applying SAEs to smaller language models. Think of them as the lab rats of the LLM world. These smaller models were still complex, but they were manageable enough to allow researchers to test different SAE architectures and see if they could actually disentangle meaningful features.
And did they? Were they able to separate the signal from the noise and find those elusive features?
They were. These early experiments demonstrated that SAEs could successfully identify features that corresponded to specific concepts, even when those concepts were represented by this distributed pattern of activation across multiple neurons. It was like finally being able to hear the distinct melodies within that complex symphony.
So SAEs started showing promise, proving they could handle the complexity of at least these smaller language models.
Yeah.
But the real prize, the ultimate test, was to scale them up to tackle those massive billion-parameter behemoths like GPT-4 and Claude, the models that were already starting to power the most advanced AI applications. Were SAEs up to the challenge?
That's where things got really interesting, and where we'll pick up in part 2.
Stay tuned, folks, because we're about to venture into the realm of AI titans. Welcome back to Talk Tensors. We're picking up our exploration of sparse autoencoders, those AI detectives uncovering the secrets of large language models.
Yeah, and we left off on a cliffhanger.
Yeah, we'd seen how SAEs showed some promise with smaller language models, but the real test was scaling them up to those massive models like GPT-4.
The models with billions of parameters, the ones that are writing code, composing poetry, and sparking all sorts of existential debates.
Right, the AI heavyweights. So how did SAEs fare when faced with these giants of the AI world?
Well, as you might imagine, scaling SAEs to these massive models wasn't a walk in the park. It presented a whole new set of challenges, both computational and conceptual.
I can only imagine. It's like going from analyzing a beautifully crafted haiku to trying to decipher the entire Library of Congress. Where do you even begin?
Exactly. One of the biggest hurdles is simply the sheer amount of computational power required. Remember, we're talking about models that are trying to extract meaningful features from billions, even trillions of data points.
It's like trying to run a high-resolution simulation of the universe on your laptop. You might get some interesting results, but it's probably going to take a while and melt your motherboard in the process.
And on top of the computational challenges, there's also the issue of ensuring that the features extracted by these massive SAEs are actually meaningful and interpretable. The problem of polysemanticity, where a single neuron can respond to multiple seemingly unrelated things, becomes even more pronounced with these larger LLMs.
So it's not enough to just find patterns in the data. We need to make sure those patterns correspond to concepts that we humans can understand and reason about. Otherwise, it's just a bunch of AI gibberish. Impressive, but ultimately meaningless.
Precisely. And that's one of the ongoing challenges in this field, developing robust evaluation metrics that can tell us whether the features extracted by these massive SAEs are truly capturing something meaningful about the LLM's internal representations.
So it's like we need a team of AI critics, not just AI chefs, who can judge the quality and coherence of the dishes being produced.
A very insightful way to put it. But despite these challenges, researchers have made some remarkable progress in scaling SAEs to these massive models. And the insights they're gaining are shedding new light on the inner workings of these AI titans.
Okay, I'm on the edge of my seat. What are some of the key findings that have emerged from these large-scale SAE studies? What secrets are they revealing about these enigmatic models?
Well, one of the most fascinating findings is that even in these massive, seemingly chaotic models, there's an underlying structure and organization to the way information is represented.
So beneath the surface complexity, there's a hidden order, a method to the AI madness.
Exactly. For example, researchers have found that certain groups of neurons tend to specialize in processing specific types of information, like grammatical structures, semantic relationships, or even emotional tones.
It's almost as if these massive LLMs are developing their own internal cognitive modules, each responsible for a different aspect of language processing. It's like the different sections of an orchestra, each contributing its unique voice to the overall symphony.
That's a very apt analogy. And what's even more remarkable is that these modules seem to emerge organically during the training process without any explicit guidance from the researchers.
So it's not like we're programming these models to have specific modules for grammar or sentiment analysis. They're figuring it out on their own, based on the patterns they're detecting in the data.
That's right. And this self-organization is one of the most intriguing and potentially transformative aspects of LLMs. It suggests that these models might be capable of developing much more sophisticated and nuanced understanding of language than we previously thought possible.
It's like we've planted a seed of AI, and it's grown into this incredibly complex and beautiful ecosystem with its own internal logic and structure.
A poetic way to put it. And SAEs are providing us with a powerful lens to observe and understand this emerging ecosystem.
Okay, so we've explored the challenges and some of the fascinating findings of applying SAEs to large language models. But let's shift gears a bit and get into the nitty-gritty of how these SAEs actually work. What's going on under the hood of these AI detectives?
Well, at their core, SAEs are a type of neural network. And like any neural network, they consist of layers of interconnected nodes, each performing a simple mathematical operation on its inputs.
Right, the basic building blocks of AI. But what makes SAEs unique? What sets them apart from other neural networks?
The key difference lies in their objective. While most neural networks are trained to perform a specific task, like image classification or machine translation, SAEs are trained to reconstruct their input data.
So instead of learning to map inputs to outputs, SAEs are learning to map inputs back to themselves. It sounds a bit like an AI hall of mirrors.
In a way, yes, but there's a method to this apparent madness. By forcing the SAE to reconstruct its input data, we're essentially forcing it to learn a compressed yet informative representation of that data.
So it's like squeezing all the essential information from a large, detailed image into a smaller, lower resolution version. You might lose some of the fine details, but you still capture the essence of the image.
Precisely. And that's the beauty of SAEs. They force the model to identify the most salient features of the input data, the features that are most important for reconstructing it accurately. And in the context of LLMs, those salient features often correspond to the underlying concepts and relationships that the model has learned.
So by training an SAE to reconstruct the activation patterns of an LLM, we're essentially training it to extract the key concepts and relationships that the LLM has encoded in its internal representations.
Exactly. And that's what makes SAEs such powerful tools for understanding LLMs. They provide a way to peer into the black box and see what's really going on inside.
This is all incredibly fascinating, but I have to admit, it's also a bit mind-bending. We're talking about training one AI system to analyze another AI system, all in the pursuit of understanding how these systems learn and represent knowledge. It's like an AI inception.
It certainly is. But this recursive, self-referential aspect of AI is one of the things that makes it so captivating and potentially transformative. It's forcing us to rethink our own assumptions about intelligence, learning, and the nature of knowledge itself.
Well said. And as we delve deeper into the world of SAEs, those assumptions are likely to be challenged even further. But we'll have to save those deeper dives for another episode.
Indeed. There's still much more to explore, from the specific architectures and training techniques used for SAEs to the ethical considerations and potential societal impacts of these powerful tools.
Right, because as we've seen, with great AI power comes great AI responsibility. But for now, we'll leave our listeners with that thought-provoking cliffhanger. Stay tuned for part 3, where we'll unveil the secret weapons in the SAE arsenal, the advanced techniques that take these AI detectives to the next level. Welcome back to Talk Tensors. We are wrapping up our deep dive into sparse autoencoders, those AI sleuths that are helping us unlock the secrets of large language models.
And we've seen how SAEs can be scaled up to tackle even the most massive LLMs, revealing fascinating insights about their inner workings.
Right, we've gone from those early attempts to analyze individual neurons to these sophisticated models that are capable of extracting high-level concepts and relationships from billions of data points.
It's been quite a journey.
It has. But as we hinted at in the previous episode, there's even more to the story.
There is indeed.
Researchers have developed some incredibly clever techniques to make SAEs even more powerful and efficient, pushing the boundaries of what's possible in understanding these complex AI systems.
Think of it as going from a basic magnifying glass to a high-powered electron microscope.
Okay, I'm ready to zoom in. What are some of these advanced techniques that are taking SAEs to the next level?
Well, one approach that we touched upon earlier is called gated SAEs. These are like the VIPs of the SAE world. They have an extra layer of control that allows them to be more selective about which features they activate.
So instead of just blindly compressing the input data, they're actually making intelligent decisions about which features are most important for preserving the information.
Exactly. Imagine having two separate teams working together. One team is responsible for identifying the most salient features of the data, while the other team determines how strongly to emphasize those features in the compressed representation.
It's like having a team of AI editors who are not only selecting the most impactful sentences from a text, but also deciding how prominently to display those sentences in the final layout.
Precisely. And this two-pronged approach allows gated SAEs to achieve higher levels of accuracy and efficiency compared to traditional SAEs.
So they're not just compressing the data, they're curating it, creating a more refined and informative representation.
Exactly. And this makes them particularly well suited for analyzing those massive LLMs where the sheer volume of data can be overwhelming.
Right. It's like trying to find a needle in a haystack. But with gated SAEs, we have a more sophisticated metal detector that can help us pinpoint the most valuable needles.
A very apt analogy. And another technique that's been gaining traction is called Top-K SAEs. These take a more direct approach to sparsity, simply selecting the top K most active features and setting everything else to 0.
So it's like having a strict AI editor who mercilessly cuts out any sentences or paragraphs that don't directly contribute to the main message of the story.
I like the way you think. And this ruthless approach can be surprisingly effective. By focusing on only the most salient features, Top-K SAEs can achieve comparable or even better performance than traditional SAEs, but with significantly fewer active neurons.
So it's another win for efficiency. But how do we choose the right value of K? How many features are enough to capture the essence of the data without losing crucial information?
That's a great question, and unfortunately, there's no one-size-fits-all answer. The optimal value of K will depend on the specific data, the complexity of the model being analyzed, and the desired level of sparsity.
So it's a bit of an art as well as a science, finding that sweet spot between compression and information preservation.
Exactly. And researchers are constantly exploring new techniques and heuristics to help determine the best value of K for a given task.
It's like those master chefs who can instinctively tell the perfect amount of seasoning to add to a dish based on years of experience and intuition.
A delicious analogy. And speaking of chefs, remember that idea of model steering we discussed earlier?
Oh, right. Where we could potentially use SAEs to influence the behavior of LLMs.
Yeah.
Like making them less toxic or more factual in their responses.
Well, some of these advanced SAE techniques are proving to be incredibly valuable for model steering. By identifying the features that control certain aspects of the LLM's behavior, we can potentially manipulate those features to nudge the model in a desired direction.
It's like having a set of control knobs for our AI chef,
Yeah.
allowing us to fine-tune the flavor profile of their creations.
Precisely. And while this is still an active area of research, there's been some encouraging progress. Researchers have shown that it's possible to use SAEs to make LLMs less likely to generate biased or offensive language, or to encourage them to produce more creative and engaging text.
That's incredible. It's like we're not just understanding these AI systems, we're starting to shape them, to guide their development in a way that aligns with our values and goals.
It's a powerful concept, but one that comes with significant ethical considerations. We need to be very careful about how we use these steering techniques, ensuring that they're not used to manipulate or deceive people.
Right, because as we've discussed, with great AI power comes great AI responsibility. But despite these challenges, the potential benefits of SAEs and model steering are immense. They could help us create AI systems that are more aligned with human values, more beneficial to society, and ultimately more trustworthy.
I couldn't agree more. And as we conclude our deep dive into the world of sparse autoencoders, I think it's worth reflecting on the incredible progress that's been made in this field.
It's truly remarkable. Just a few years ago, the idea of understanding the inner workings of these massive language models seemed like a pipe dream.
But thanks to the ingenuity and dedication of researchers, we're now starting to crack open the black box, revealing the intricate mechanisms that drive these AI systems.
And as we continue to explore this fascinating frontier, SAEs will undoubtedly play a crucial role in shaping the future of AI. So that's all for this episode of Talk Tensors. Thanks for joining us on this deep dive into sparse autoencoders. We hope you learned something new, and we'll see you next time for another exploration of the cutting edge of machine learning.